I'm just writing what we finished yesterday, this part, okay? So you are not late. So the solution was like 1, 0. And I gave you some questions, I remember, yeah? About the second solution. Do you remember? It was traffic lights. So the light now is green. So what happens? So the first solution. Fine. Thank you. Thank you very much. So the first solution was that nobody moved. Okay. And we checked that this is a weak solution. Okay. It satisfies remember, in this domain, the function is C1. So we have to check that, okay, it's a constant, so it's C infinity. So it satisfies this equation in this strong sense. It's classical solution in this domain, okay? Also, we checked that it's classical solution in this domain. And there is some discontinuity. We have to check if it satisfies the famous Rankine-Hugoniot jump solution. There is some discontinuity, but with respecting some speed, which is sigma, and sigma, if sigma, and this is the discontinuity here, this is sigma time. So sigma is 0, okay? So sigma must be f of 1 minus f of 0 divided by 1 minus 0. So it's 0, so it's okay. This is fine. It's a weak solution. And I gave you another one. It was about the military parade. Do you remember? You have this in Filipino? Yeah, some military parade sometimes? No? Yeah, I think. Every country. So u of xt. Okay, so it was, maybe I can. So remember, so I wrote it yesterday. So should be fine if okay, I maybe put it here. Sorry, okay. Why put this? And this is at time equals to, this is a solution, time equals to 0. Solution 1 is this one. And okay, this is the same. Sorry, this is u of x time. Solution 1. And solution 2 is, remember, solution 2 is something like this. One here, so 1, 2, 3. So in this case, okay. So we have some part going, okay, this line is going back, okay. The discontinuity is going in this direction, and you have one discontinuity here going in this way. And so the solution, maybe I took u equals to 1 here, the density is, and maybe took 1/2 or 1/3. Yeah, but you can change. Maybe yesterday I took 1/3, no? 1/2, okay. But you can, as exercise, you take another value, and it works. But what change is the speed of this front, okay, the discontinuity, okay. So this what it was, u of x time is equals to 1 if x is okay, sigma 1 t. This is I ask you to find sigma 1, and 1/2 if x between sigma 1t. So the equality is exactly the line of discontinuity, sigma 2t, and 0 x bigger than sigma 2t. And I ask you what is sigma 1 and sigma 2, okay? So in this, sigma 1 is negative, necessary. You can see it, okay? This is sigma 1, the slope. This is time, this is x. And you have sigma 2 here. So did you compute sigma 1 and sigma 2? It's not Python. Huh? Just you need one pen and 30 seconds. Hmm? So what is sigma 1? Hello? What did you calculate sigma 1 and sigma 2? Yeah? No? Yeah, because many things to do. So how I can calculate sigma 1? So here is 1, 1/2, and 0. So this is, for sigma 1, u left, the left state is 1, and the right state is 1/2. Here, the left state, not the same, is 1/2, and the right state is 0. Okay? You have to look at the discontinuity in this sense. So sigma 1 is f of 1 or 1/2, it's the same. Okay? 1 divided by -1. Okay? What is the result? It should be negative. It must be negative. Yeah? So what is the value? F of 1 is 0. Okay, if you would put f of 1 divided, it's the same. F of 1/2 is 1/4, yeah? Divided by -1/2, so is -1/2. Yeah? Fine. So sigma 1 is 1. So give me sigma 2. Sigma 2 is positive, we can see. Maybe it's 1/2. It's the same, no? Maybe. But plus. So sigma 2 is f of 0 minus f of 1/2 divided by 0 minus 1/2. So plus this one. So this is minus. So this is 0 divided by -1/2. So this is 1/2. Okay. Because I took 1/2, so this is the same speed, but opposite. Okay, the front is going like this, and this one. There is some symmetry. Okay? Fine. Now, I told you that there is another solution, which is, I give you this is solution 2. So now solution 3. Is u of x time is equals, to 1 here, 0 if x is less than minus t. And 1/2 by 1. And 0. Okay. So the solution is not constant. Okay. So in this case, you have, I can put it here maybe. You have something like this. Okay, but Okay, something like this. So if you want to, so when x is equals to minus t here, you will have 1 plus 1 divided by 2, so it's 1. So there is, it's continuous here, and also when x equals to time, like divided by time is 1, so 1 minus 1 is 0. So there is no discontinuity. The solution is like this. I put so first it was 1, okay, like this, 1, and 0 here at time t, minus t, and you have this. This is the third solution. Okay, that's fine. So this is called a rarefaction wave, and this is what usually you see. Okay, when there is traffic light, so the first car begins starting first, and after the other. So the first has some is in front of. So the first one is going faster and faster, and the second one is saying the first one, so he increases the speed. So you have something like this. So this is like elastic thing. So you have some, we call it a rarefaction wave. We have seen this is in the movie. Okay, so the first one is going faster and faster. Okay, this is, I think, what happened. Okay, in some special condition, but if there is only this, drivers are okay. This is what happened in the traffic lights when you have the green light. So, yes, so what we have, so this is, if you put it in the, so what happened here, you have some D1, domain D1, you have 1 here, you have 0 here, and okay, this is a rarefaction wave. So it's not discontinuous, you have some expression, some, how we say, self-similar solution, depending on x over t. I didn't know if you know this term, self-similar solution. Sometimes you have like traveling wave, like, okay. Anyway, so, and we do this, like representative of what is rarefaction wave. Okay, it's not, okay, this is maybe sigma 1 and sigma 2. So there is no discontinuity here, because it's sigma 1, this is x equals to minus t. We say that the solution in this way, it's continuous, okay? We said if you x equals to minus t here, the limit x divided by t is minus 1, so it's 1, okay? So there is no discontinuity, okay, because you can see here at time t what happened. So, but what we have to see is that where the function is C1, there is, okay, if there is discontinuity, you have to check the Rankine-Gonyou jump relations. Here we don't have this, no discontinuity. But we have where our function is C1 here, and C1 here, not globally C1, piecewise C1, okay? So we have to check in D1 and D2 and D3 that our solution satisfies this simple equation in the Chrank sense and the real derivative, okay? So in D1 and D2 and D3, it's a constant function, u is 1, you put 1 inside, it works, gives 0, no problem, okay? Now in D2, you have to do some calculation. So u of xt is this one, so you have to calculate this part, okay? So we need this 1 minus 2u du over dx, the question, okay, we have to get 0. Okay, so let's do it together. So this is u of xt. What is the derivative? Du over dt is, or this is the domain d2. What we get? Yes? differentiate this with respect to time. Yeah? That is 1/2. Divided by T2. Okay? Now I need 1 minus 2u multiplied by du x is 1 minus 2u. So minus 2, it means minus 2 this, and minus 1 minus 1, so you get x over t, I think. Yeah, this part. And du divided by dx, here we get minus 1 over 2t. Yes. So this is min x, 2t, sorry. So this is min x over t2. So the addition gives you 0, 2x. Yes, plus equals 0. That's plus this, 2, sorry. Okay, so it works. So we satisfy, there is no discontinuity, and in D1, D2, and D3, our selected chosen function satisfied the classical, the equation in the strong form, in classical, as classical derivation. So then U3, solution 3, is also a weak solution. Okay, fine, easy. I think easier than what you did before. Okay, fine. So this is something very, very nice, very easy to understand, because this you can see this. And now we have the problem. Okay, first we have some. We studied the method, the characteristic to see the smoothness of the solution, and then we say, well, you have some discontinuity, so we have to give some weak formulations. Okay, so we did to get some weak solution, but now we have another problem. What is the another problem? We have many weak solutions sometimes. There is no uniqueness of weak solution. Okay, so we have to select what is, because we say a problem is well posed, at least we have uniqueness and existence and continuity with dependence with respect to initial condition. So here we have existence, but no uniqueness. So I have to select what is the good, maybe some, what is the good solution. So it depends, because we have discussion with Joachim yesterday. And okay, if it's a paramilitary, so this is, and the speed is imposed, you can see this is physical solution, okay? But okay, this is all one also accepted, and we will see. Okay, we have we'll add some criteria to select what is maybe a nice solution, what we call physical solution. So we will see that in this case, this one will be selected. Okay. So now, I will give you what is the criteria of selection. It's the entropy selection. Okay, so entropy pair or criteria. Okay, so remember we did this entropy solution. We did this for the system, so now it's easy. So remember the definition of entropy couple. Eta and psi is an entropy pair of the equation sorry. Okay, no, it's okay. So when we speak about weak solutions, we only use the conservative form. So for systems that are not conservative physically, if you have a model initially is not conservative, So we have a big problems to define what is the weak solution. So for continuous, for smooth solutions, okay, we can take some mathematical model with in non-conservative form, or maybe for systems we cannot put it in a conservative form. But when we speak about weak solution, it's only for conservative. Okay. So if you have some discontinuity here, so it's like a heavy-side function. The derivative of heavy-side function is a Dirac. This is defined. But if you put A of u multiplied by dxu, you have some heavy-side multiplied by Dirac. There is no definition of this. We don't know what is this. Okay, so they have problem. But all physical problems generally are in this form, even for systems. But we say, mathematically, we can put it in some non-conservative form and depend on the variable. I give you some about the shallow water problem. If you take the variable square root of h and u, remember, and I think the system, you cannot put it in conservative form. Maybe somebody did this. It's very easy. Okay, just to say what is the convection matrix A of u. Okay, with the depend on the variable. Sometimes conservative, sometimes HU is conservative, HU is conservative. But if you take like mathematically square root of h and u, you will see that it's not conservative. But physically, we use the first one because this is the physical model. Okay, so is an entropy pair of this if, okay, two conditions. So eta must be eta convex. Remember? Okay, so let's take smooth function. Convex you can, right? And there is some relation between eta and psi. What is this relation? Here eta prime is not a vector line, or it's a real, okay? So what we have here, second condition, eta prime by f prime called psi prime. And we get it by multiplying this equation by eta prime. Eta prime du of dt plus eta prime f prime, and this must be psi prime, okay? So remember, if u is smooth, then multiply this equation by u du over dt plus eta prime of u f prime of u du of dx equals to 0. See, this is psi prime, okay? So, and then you get something like, in conservative form, everything is smooth, okay? And this one, but only for smooth solution, smooth, okay? So example, so what is for the systems, I just give you one example of entropy pair for the shallow water model. But here, real function, because it's difficult to find for systems what is eta and psi, such that you have some kind of relation. It's not easy, okay? We say it's not the multiplication. This multiplication is not necessarily the gradient of some function. If you have many variables, but in R it's okay. So you take, finally remark. So you take eta convex. If you take any eta convex and psi, you take just the primitive of, because you need this. So this is a real function. So we say we need psi prime equals to something. So psi eta prime f prime. So you have infinity. You can construct infinity. If you take infinity eta convex, easy. So infinite possibilities. Possibilities, maybe, okay. For example, if you take eta of u is u2 over 2. It's not burgers, but just okay. So you need that. So this is the second derivative is 1. So it's positive. So eta is convex. Okay. And so you have just, in our case, eta prime of u by f prime of u. See, eta prime of u is u multiplied by 1. Okay, this is f prime. Remember? For traffic flow. So you need to calculate the primitive of this. So you can take psi of u equals 1/2 of u2 minus 2/3 of u cube. You can add the constant if you want. Okay. You give me eta, I give you psi. Okay. Easy. This is an example. You can check with other examples. It's easy. Nothing. So now definition. So if u is a weak solution of the equation u equals to 0, okay, that means remember the weak formulation with integral multiplied by phi. Imagine that you get like before. We have many weak solutions. We say that u is an entropy solution if the equality that you have seen here, this one, is negative. It's not 0, negative in a weak sense. Okay, I explain. It means that for all phi at support compact support plus infinity and phi positive, got the sign if you change phi by minus phi, sign doesn't mean anything. So if you take a positive function multiplied by this, will be negative. So doing the integration by part, it means that you have something like this. Eta of u plus psi of u x on r plus here. Dx dt is positive, it's negative. Because integration by part will give you minus, this one is negative, so this is what is entropy solution. So you have something like this with equals to 0, but with u and f of u. This is weak solution, but you have to satisfy this, okay? And it's very strange, so don't worry, we will not pass much time on because it's maybe complicated. Because why? How we can do this? It's not easy, but I just give you the result. People work on, can give you references if you want to understand more. So we are interested in C1 function, and okay, there are some. So this criteria is a weak solution one. Okay, so if you have this, then we have some existence and uniqueness of the solution. Okay, I will give you this theorem, no proof. It's not our interest today. And after I will give you just for the Riemann problem, that we say you have some discontinuous initial condition, what is the entropy solution in each case? Give you this one, in this case. Okay, there are many things between, but we have no time, okay? So the theorem said, so this theorem is due to Khrushchev, like this, Russian, he died. I met him many years ago in Portugal with Joachim, but he died maybe 2 years after. Okay. So if U0, we take initial condition which is bounded, that we are interested. For example, U is bounded between 1 and 0. That's fine. If U0 is in an infinity and the flux F is C1, we need some regularity on the flux, C1 from R to R, okay? Then the Cauchy problem equals to 0 and U of x0 equals to 0x has a unique weak entropy solution. Weak solution, of course, but in addition, satisfying the entropy criteria. Entropy, a unique weak entropy solution, U, which is also in R, an infinity of R multiplied by 0 plus infinity R. So if you have a smooth solution, it's also automatically a weak solution, but the contrary is not okay, okay? All smooth solution is weak. So you have, like for example, we study first by the characteristic method. So we begin until sometime T star, and then after we will not have strong solution, but we continue maybe like a shock wave, something like this. So we have some, we know just that the solution is bounded in our case, okay? So it works. This is good to define what is global solution. There is no T star. T star only if we have smooth solution. If we begin with smooth solution. Sometimes we begin with U0, which is discontinuity, like the traffic lights. So there is no T star. But you have existence of a global solution, okay, defined for all the time. This is fine, okay? So now, let's see what happened in our case, which is the Riemann problem. Okay, now. So I don't put more time for this. Riemann problem. I just give you what is the solution in this case with some discontinuous initial condition with two constants, UL and UR, only two constants. Maybe this way, okay, because if not, okay, you have to play with characteristic method and other things. So the Riemann problem is this one. Well, so Riemann problem is the Cauchy problem U0 of x is something like the UL left from where for x negative and UR right for x positive. Okay, so maybe, yeah, strictly, because at 0, something like this. This is very interesting in this kind of, this one, or maybe the contrary, okay, or this one. You will see that this is important to see. If we have seen for the traffic lights, okay, in which case we will have okay, discontinuity, what happened, okay? So remember, this is for traffic lights, this is 1 and 0, and we have seen that And when you have green, normally it's not shock wave, it's rarefaction wave given by something like this, okay? But in this case, it means here, maybe like we take first, it's 1/3, remember with the bottle, 1/3, and they stop it at what time? At some time, and then this is a shock wave. Like we have seen the cars arriving, they have to stop suddenly. So you have some front going at the left, okay? Remember. So this is called the Riemann problem. It means that your initial condition is like this, okay? So I will give you what is the solution of this, okay? And u of d time plus d of dx equals to 0. So theorem. So assume in the case, assume that f is concave, because in the case of traffic flow, f of u is like this, remember, between 0 and 1, so it's concave. Because it depends if your function flex is concave or convex, you have to reverse the form of the solution. This is the convexity of the function is important. So f concave. I don't know if there is a e. Yeah, I think yes. Not sure. In French, there is. Okay. So first, assume that if UL left, so in this case, UL is less than UR. Okay, like UL is 1/3 and UR is 1. Because cars are stopped and the other are arriving. So in this case, we will get the entropy solution is this shock wave. Okay, so the entropy solution of, say, maybe Cauchy problem of the Cauchy problem is the shock wave given by u of x time. So is UL and UR for what here? What I put here? For x, yes, x less than something. The equality corresponds to sigma. You know, the Rankine-Hugoniot, it's the speed of the shock. Like we have seen maybe 1/2 and 1/2, minus 1/2 before. So here I put sigma t. Yeah. X equals to sigma t is the discontinuity. Okay. And here x is bigger than sigma. Okay, bigger, maybe less. Okay, because there is discontinuity. So it's the same. I will show you maybe where sigma satisfies the Rankine-Hugoniot jump relation. What is sigma? How we calculate sigma? You know UL, you know UR. Sigma is no, there is no derivative. No. Yeah, dx of dt for the. How we calculate sigma? We did this first. 1/2 minus 1/2. Yes, f of, you know you have the flux, you know everything. So f ul minus f of ur divided by ul minus ur. Okay? Only this. So in this case, so your initial, okay, put two theorems. Maybe after I put the others. Maybe in this case, okay. So this is initial condition. If you have this, and after you will get, no, it's contrary. UL is less than UR, okay. This is your initial condition, and after you will get this. Okay, so this is 0, this is sigma at time t. Okay, first it was 0, now it's at time t. The discontinuity is exactly at this time. Okay. Now, if the contrary UL is bigger than UR, so the entropy solution, it's not this, because this is a weak solution, even if UL is bigger than UR. This you see, okay, it's a weak solution, satisfies here, and discontinuity sigma, but it's not the entropy solution that we have seen. Entropy solution is, so this one is shock wave. The entropy solution is the rarefaction wave. So what is rarefaction wave? It's something like the solution number 3, okay? So you have something, here is U left, for X less than, so it's continuous. So F prime of UL by time, it's not sigma, sigma is the derivative, and UR is X bigger than F prime of UR time, and between this, in this area, UL, the solution is something self-similar, depending only on X over T. So what is U? Capital U is F prime minus 1. Okay, so in this case, the solution, this is UL is less than UR, and if UL is bigger than UR, so the initial condition is like this, and after, okay, it looks like this, so it's continuous. Okay, so this is the theorem. I give you example how we calculate this. This is F prime, so why? Okay. What is U? Calculate U. So what is why necessary is F prime? Because if you use the equation, you say, okay, U of X time is something like this, depending only, say, maybe call it, we call it sigma, but sigma is not the Rankine-Gogno formula, okay? So, sigma is X over T. So what is du over dt? Imagine you know your capital function U. We are looking for capital U, and we'll see that U is necessarily this function. So the derivative of this is, I will help you, minus X over T squared U prime. Okay. And what is so f prime of u and du of dx. So f prime of u is f prime of u. And du over dx is, yeah, 1 over t multiplied, sorry, by 1 over t and u prime of sigma, right? So we have to, this is must be 0. So here we obtain, we can put 1 over t in front of, so this is, you have minus x over t, this is sigma. U prime here, sigma plus f prime of u of sigma by u of sigma, this is 0. Okay? So this one must be 0. So the function f prime composed with u is the identity function. Okay? F prime of u of x is x, minus x equals to 0. Then u is f prime minus 1. Okay? So we'll see that the function I gave you, we calculate it by this way. Okay, we take just the inverse function. I will show you. So example, if f of u is 1 minus 2u, we call it v. What is the inverse? So u is equals to 1 minus v over 2. This is f minus 1 of v. So u, capital U of sigma is, this is the expression, is 1/2, 1 minus sigma. So remember, this is what I give you before, exactly. Okay. So for so solution 3 equals the entropy solution. Solution in the example. Because in this example, we are in the situation exactly this, because here we had 1 and here is 0. So the theorem told us that if you need to see what is the entropy solution, it's this one. So yesterday discussing with Joachim, he said, yeah, this is a physical, generally it's physical, but if it's a military parade, it's not maybe the physical solution this day. Okay? But this is criteria, and there are many things about fast transition where this criteria is not the good criteria. Okay? Okay, and for the shock wave, this is what we see for the first example. You know this one, when I use my bottle with water, what we see, what you can see is exactly the entropy solution. Okay. This is for this is condition 1 and 0, and also when for this 1/3 and 1, the entropy solution, entropy solution, where in this case 1/3 is less than 1. So is the shock wave is u of x time is equals to 1/3 at the left, but x less than sigma time and 1 for x bigger than sigma. And sigma is, I didn't remember, but f of 1/3 minus 1 of 1 over, so f 1/3 is 1/3 by 2/3, I think 2/9. So it's negative sigma, okay, remember, the cash arriving, and minus 2/3, so it's minus 1/3, okay, so this is my third sigma. So this is the entropy solution, but this is it's easy to understand. Okay, you have to stop immediately if I have time, but I think I will not have time to show you what is the movie, but I give you maybe the link. It's easy to get it in internet. You put shockwave cars, experience something like this. Okay, fine. Just a remark. Yes, no, I didn't finish. Now, this is when we have concave function. So in the case, yes, I have to show you something important. If you see this, okay, for example here, just the f prime is 1 minus 2. So if you have the convex function like this, okay, so we say we are in UL less than UR. So imagine that UL is here, U left, and UR is here. It is important to see what is the derivative here. So f prime, if UL is less than UR, f prime of UL is bigger than f prime of UR. So if you want, you write, what is my equation? If you want this part, it's like advection function, equation, sorry, but with the speed c, which is f prime of 1, and f prime is 1 minus 2, so it's minus 1. And I said, no, yeah, we have, so in this case, we have the speed here is minus 1, and the speed here is 1. So this speed is going faster than this. This is what we have rarefaction wave, okay? But in this case, the speed here, if we take 1/3, for example, this is maybe, for the example, is 1 minus 2/3, so it's 1/3. And here, this is just for the example. 1 minus 2, so UR is 1, so it's minus 1. Okay, so I'm in the situation. So the left-hand side, in this case, is going faster than this one. Okay, and if you try to see what happened for the characteristic, this is sigma. So the characteristic is 1/3 here. Sigma is minus 1/3. Okay, well, so but I want it's the same in general case. Okay, you have sigma like this. Okay, and minus 1/3. This is 1/3 here, this part, and the other part, the sigma here is maybe 1/3, and this is minus 1, and this is minus, the speed is this one, the slope of this function, sigma. So sigma is bigger than this derivative, in this case it's negative, but less than this one. So sigma is less than between f prime of UR and f prime of UL. And this is called the lax entropy conditions. And this condition is important to say that is we have an entropy shock. Okay, if you need an entropy shock at the left, you need to have speed bigger than the speed at the right. Okay, not the speed of the vehicles, but this is the velocity, the speed of the equation. Okay, so this is important. Yeah, so now if you take a convex function, oh, better, convex function. For example, you have burgers, like burgers, FU2 over 2, okay? Burgers equation, it's a case. Because usually if you look at internet, when they study this lecture, like this, they use more burgers than traffic flow. But I wanted to see this way, to show you some, because it's a nice application for traffic flow. Burgers can stand maybe for the fluid, but so now you can complete your study. If you take burgers, you will understand. But there is different thing because burgers, it's convex. So we change all. So if UL is bigger than, is less than UR, you have the same thing, but you get some rarefaction wave. Rarefaction wave, okay? Because now the speed for burgers, for example, is U by UX. So U, this is speed. The speed at the left is less than the speed at the right. So rarefaction, okay? And the contrary, if UL is bigger than UR, and you can see that is, if F prime is increasing, so F prime of the left is bigger than F prime of UR. So we respect this. This is condition even if you are concave or convex. The speed at the left, you know, F is convex, the derivative F prime is increasing function. So if you are UL bigger than UR, then in this situation, this one is going by speed U, so UL is bigger than the other, so it will push the other part. This is a shock wave, okay? And sigma will be between. This is a shock wave. Okay. And now, just to show you what happens. So this the same picture. This is available. This is NEF. Okay. So just I want to show you what happened in the case of the advection equation. So this is convex, concave. Now look at ut plus c of dx equal to 0. So here f second is 0, okay? The linear case. And you take Riemann problem also. So theorem, yes, F linear, maybe you can put theorem F linear. So be careful. If you are not convex, you are not concave, it doesn't mean that you are linear, okay? Like a positive function, negative function, that is 0. No, complementary. You can have some function with positive, negative. So you can have some function like U cube. U cube is not convex, is not concave. Convex in some part, but okay, we don't treat this case. It is only the extreme case, concave, convex, and linear, okay? So what happened in this case? So theorem, the weak solution, the weak entropy solution is called the solution u of x time is also u0 of x minus ct. The same, even for if your initial condition is a discontinuity, so it's ul if x less than ct, if this negative, and ur x bigger than ct. But it looks like a shock wave. But this is not a shock wave. We call it, I will explain you why. Call it a contact discontinuity. Okay, I'll explain. So what happened? So imagine that this model, you have some cars, like this. Maybe some discontinuity initially, and here the u is less, maybe. But imagine that, okay, it's not the model of f of u is only cu. So all the cars are going with speed c, the same speed. It's not the model f of u equals to, okay, not. Okay, it can happen. Okay, so, okay. If there the density is big, it's not a bit. Sometimes in the highway, you can have some. The density is bigger, not too much, but okay. Everybody is the velocity here maybe is 70 kilometers per hour, and also here there is more space, and everybody is moving at the same speed. Okay, it could happen. Okay, so what we get is, if you take the image, is you have the same image progressing. Okay, so it looks like a shock wave, but it's not a shock wave, because here is not, there is no transfer from this to this. When we get the shock wave with the fluid or the cars, first case, we have some front going at the left, but the cars is coming from the left-hand side to the right-hand side. Remember, okay? When first they were like this, the other are coming, but after this one, so the discontinuity is here, and after the discontinuity is here, and this one is doing. So there is some transfer. Okay, and this is due because this one has an effect of this one, paralytic. But here, everybody is driving at speed c. So it's not a shock wave. There is no influence from this part to this part. It's just discontinuity. Everybody is maybe walking or, so it's not a shock wave. It's just discontinuity. It's an image. No problem happens. Nothing happens. Everything is moving at speed c. Okay, so it's not shock wave. And if you see the characteristic, if you do sigma, sigma is f of u, ul minus fur, etc. So the discontinuity, okay, we put like this, and all the characteristics are parallel. They don't go. If it's shock, it means that the characteristics go through the shocks. You need information from the initial condition here and here to go to the shock. This is a shock, and there is some transfer. Okay, transfer of here. There is no transfer. Okay, they are not affected by this, and vice versa. Okay, so this is important to understand what is a shock wave, not shock wave. Okay, so I have maybe 20 minutes before finishing. I will tell you what happens for the case of system. Okay. The difficulty is not the same, but I will give you some idea. So finish for the scalar. Okay, I didn't tell about it. What happens if f is not convex nor concave? Okay, we can. There is the theory is clear in this case because we have scalar equation. But for systems, many things are more complicated. So just coming back to the systems. in a few minutes. So definition, remember, okay, U of dt, also in a conservative form, okay? W, I call it W, okay? For the system, equal to 0. So, and we assume the system S is strictly hyperbolic. Hyperbolic, strictly hyperbolic means you have some separate speed and speeds different, okay? And conservative form. Really important. If not conservative, the Riemann problem, we don't know. Okay, so definition. We say that the K characteristic field is genuinely, I'll write it genuinely, I think this, non-linear, very strange, non-linear, GNL, if for all W in the interval, in the domain where we are physical domain, you have something like gradient of lambda k of W multiplied by Rk of W different of 0 for all W and omega. Okay? So genuinely non-linear. We see that this definition corresponds in the scalar case that either your function is, maybe you have your function is convex or concave in the direction of Rk. Because you have many eigenvectors, many directions, but in this direction means the second derivative, we'll see that it's not 0, okay? And we say that the same, the K characteristic field is linearly degenerate LD if the other extreme is for all W the gradient in the direction of this is, remember, this is the eigenvector, okay? Eigenvector here is R1. This is R, sorry, my R is not beautiful. You can put is 0. Okay? So just to show you that this corresponds to the convexity. So in the, if n equals to 1, so our equation is there is only dt, this is plus f prime of u du or dx, so you have one matrix 1 by 1, so this is lambda 1, there is only lambda of u, only one eigenvalues. So what does it mean? What is the gradient of lambda? So it's the derivative of u, so this is f prime prime, and the eigenvector one of u is 1. Okay, we are in dimension 1. Okay, So the gradient of lambda u multiplied by R1 R of u is only f second of u. So GNL here, it means either f is convex, this is never zero. Okay, so either in the interesting case, all the time is convex and all the time is in the direction k. You have many directions, remember. Okay, f is convex or f is concave. Maybe there is E, I'm not sure. Is there E? No? Concave? No? Okay. Okay, so we are in the conditions. And so this is GNL, means this, okay? Now the second case, okay, means, so for in the case in the direction K, RK, sorry, and this by idem, the direction RK here, okay, because you have many direction, many eigenvectors, so in direction your function is concave, convex or concave. Okay, it depends on that. And how we say, and what is linear degenerate? This is LD, okay, in for dimension 1. So it means that the gradient of lambda of u, of, sorry. So this is exactly f second of u equal to 0. So for dimension 1 is, it means you have f of u is c of u plus d if you want. But this is only, so this is that are the interesting cases. We assume we will, you know, the interesting case are this one, because if you have this is change of sign, etc., there are the difficulties increase. Okay, so the corresponding case of convexity or linear case, this is for systems. These are the definitions. And you can have maybe the direction R1 some convexity and the direction R2 something like this. So it doesn't always mean linear. Okay, but for n equals to 1, there is only one case is linear. But be careful. When n is bigger than 1, doesn't mean not necessarily linear. Okay. Yes, time is increasing. Time never decreases. So just maybe I will shift many things to give you what happened in the for the so for the case of shallow water. Sorry. So shallow water, remember, okay, the equation. So lambda 1 it was u minus square root of gh, and the lambda 2 is u plus square root of gh. Also, if you work with w, and w is h and hu, okay, h and m, then the gradient of and R1, sorry, so it is so m over h minus square root of gh, and this is m h plus square root gh, and the eigen vectors, we can calculate them. It's a 2 by 2 matrix, easy. So is 1 and lambda 1, m over h, and R2 is 1 lambda 2, so m over h plus h. So the gradient of lambda 1 is, so you have to differentiate it with respect to h, so this is minus m of h2 minus 1/2 square root of g over h. Okay, and we derivative with respect to m is 1 over h. Okay, and gradient of lambda 2 so is looks like plus 1 h and 1 over h. Okay, so if you compute the gradient of lambda 1 scalar R1, I have a colleague his name is R1. So you have to multiply this by this, and okay, this is 1 by, so it's this one plus this one by this one, so m over h2 will disappear, and normally you will get minus 3/2 square root of gh, so it is never be 0. So we have something interesting, so we have convex or concave case. So, but here we are in, okay, the same, the gradient. So normally you will get the same. So the notion of convexity or concavity in dimension, in this case, okay, because in dimension 1, R1 is 1, but if you change the unit is -1, which is concave, becomes convex, okay? So if you need, that is this positive, that is a negative, you see, oh, this is concave and this is convex. No, you have just to change the eigenvectors, you can change it, okay? So if you let this vector, it means that your function, your lambda 1 is concave in the direction of this R1. But if you put -1, you will get something positive because you change the direction. It means, yes, that the lambda, you have this positive, means that lambda is increasing in the other direction, not the first one. Okay, so convex, concave, it is the same. You have to change. Even in dimension 1, if your function is like this, but unit, you say my unit is this, in this direction, if you concave becomes concave. No, concave becomes convex and vice versa. Okay, so this is, here we can choose R1 such that we have exactly 1. We have to divide R1 by this quantity, and the product is 1. Why not? Exactly, like burgers, U2 over 2. Even for this one, if you change R2, then you will get exactly 1. So both, so the n characteristic and 2 characteristics are G and L. Okay? That's fine. It's like convex. Okay. So, what can I say? Just maybe a few minutes. So what is rarefaction wave? Rarefaction. See what is rarefaction wave and what is shock wave, rarefaction wave. So you are looking for something W of time is equal to U of X over time. And in our case, the W over d time is minus x over t to u prime, like before. And dw over dx is 1 over t u prime of sigma, but you multiply this by a of w, the Jacobian matrix. Okay. So if you addition is 0, so the same thing, you will get a of u multiplied by u prime of sigma is minus sigma u prime of sigma. So this is must be 0. Okay? But now it's more difficult because this is a matrix. Okay? And this is a vector. So the matrix multiplied by the vectors, it's equals to sigma by u prime. So, okay? Then it means that sigma is some eigenvalue of the matrix, and u prime is some eigenvector necessary. Okay? So in dimension 2, we have two, maybe if we have n curves given by, because u prime of sigma is something like, is in the direction of like this. So if you get, imagine that n equals 2 in the case of shallow water. So you have maybe R1 is like this. Imagine that R2 is like this, and then you have two curves. That it means that in these two curves you can join any point in this. This is we call maybe Riemann invariant. This is curve for rarefaction. Maybe from this point, this is WL to some WR here. You can get some rarefaction, and the same here. This one. So you have to be careful because if we choose R2 equals to 1, it means that because for our rarefaction wave, x over t must increase. So we are interested in this part, okay, for WL to going this one or here also. Lambda is increasing in the direction of R2, not if you want in the, remember when you get some concave function. So rarefaction, you need in this case you will get a rarefaction. So this is your WR, and the rarefaction is all this path. If you go in this part, you will get some shock wave. Okay, so you have just half. And also we can define, this is we can give explicitly a curve for the shallow water equation, just to finish. Okay, for the shock wave, so shock wave, we have to define what is this sigma by WR minus WL. And for example, for the shallow water, so you have to write H, okay, maybe W is this, H, so it's HU, I think. Okay, you need HU minus HL, L equals to sigma H minus HL, and you have the second equation. This is h of u minus h of, oh, it's m, okay. And here you have hu2 plus 1/2 gh2 minus the same hl ul squared plus 1/2 gh L squared. And combining this, we get some two curves. Maybe m is equal to some expression. You have two expression. M is a function of h, etc., and something plus minus. You can check. Okay, so we'll get some two curves, and the two curves will be also like this. So maybe this is R1, and this is R2. Maybe you get some two curves like this. You can get an explicit formula, okay? But in this case, remember the shock wave, you need that the speed at the left-hand side must be bigger. So the interesting part is this one, so this one is not interesting, okay? Because lambda is increasing in this case, and we need that lambda decrease. The speed at the left is bigger than the speed at the right. Okay, just something like this. This is the interesting part. This is R2, and this is the interesting part. And you will combine this with this. And okay. And if you get some WL and WR, not so far, then you can combine this kind of connection between this and the other point by following these curves. Rarefaction, if you go in this way, shock in the other way, but not exactly the same curve, something like this. Okay, so the combination for the Riemann problem. Combination of rarefaction and shocks. In dimension 2, you can have rarefaction plus rarefaction, rarefaction plus shock, shock plus rarefaction, or shock plus shock. Okay, you get something like this. So I think well, I have to maybe because the time. Very sorry. Okay, I just give you some idea and to show you what are the difficulties for systems. If you have understood what happened in dimension 1, it's okay. You can follow. I can give you some references about this. Okay, so I will stop here.
Thank you so much for that.